Hello, everyone, and welcome to part 3 of 3 of the notes on chapter 8. And in part 3, we're going to be discussing center of mass, or if you're British, centre of mass. Please refer to page 19 of your note packet. So, to this point, we've studied systems that are balls or blocks or things that are fairly regular in shape. But how do you deal with something like a baseball bat or indeed the bird that we saw on the previous slide, where you have something which has a more complicated shape? The way that you handle this is using the concept of something called the center of mass, which is the point that moves as though all of the system's mass were concentrated there and all external forces were applied there. So for example, if we are flipping this baseball bat through the air and it is undergoing some rotational motion, as shown here, how do we handle the trajectory of that bat, or how do we predict the trajectory of that bat? We take a look at the center of mass, and we say the way that the center of mass is moving is the way that the entire bat is moving. That's also going to be important when we start talking about rotational motion, where you have rotation about that center of mass or around that center of mass. So it's a very useful concept for dealing with more complicated shapes. Another example of this is, let's say that we have two particles and they're connected by a massless rod in a uniform gravitational field. The place where we would have to locate our hand or some kind of pinnacle in order to get these things to balance out would be called the center of mass. So the center of mass is a mass-weighted average of all of the points in an object or set of objects being treated as a single system. So you can, as we will see, be talking about 2 or 3 different particles, and if those 2 or 3 different particles are moving as kind of a set or moving in sort of the same direction in the same way, you can actually treat those particles as if they had a common center of mass. So this is a useful concept for dealing with not only things with complicated shapes, but with multiple things and seeing how they all behave as a system. And when I say that something is weight averaged, basically something that has more mass is going to pull the center of mass closer to it than a bunch of smaller points with a lesser mass. So if I have, for instance, a basketball up here, and it's really big and massive, maybe not a basketball, let's say a bowling ball, something of rather large size and weight, and I put a couple of ping pong balls on either side of it, the center of mass, as you might imagine, is going to be closer to the bowling ball than it is to the ping pong balls. So that's when I talk about something being a mass-weighted average. Things with more mass weigh more heavily in that average. So let's consider a situation where we have a bunch of particles that are strung out along the x-axis. So we have particles 1, particle 2, all the way up to particle n, located at position x1, x2, all the way up to xn. The total mass, or big M, is therefore the sum of all of these individual masses. And the location of the center of mass is going to be given by this formula. X center of mass is equal to mass 1 times position 1 plus mass 2 times position 2 plus however many objects you have, all the way up to mass n xn divided by the sum of the masses of the individual particles. So if we have, again, mass 1 with a distance of x1, mass 2 with a distance of x2, the center of mass is going to be somewhere over here at this position xcm or xcom. And we can imagine extending this to an infinite number of particles out along this x-axis. Incidentally, when you're dealing with some kind of an object, when you're dealing with some sort of solid object like a ball, you can think of that as being an infinite number of infinitesimally small particles, all of which are contributing to the center of mass calculation of that particular object. So if you take this down to an atomic level, you've got all of these atoms in one direction on the ball, all these atoms on the other direction of the ball, in this kind of big circular shape, and the center of mass of all of those atoms is the center of mass of the ball. So even though this might seem a little esoteric, in a way, that's what we're doing even with solid objects, is we're summing masses and positions of a bunch of infinitesimally small masses all set right next to each other. Okay? So in 3 dimensions, another way of writing what we just wrote, so if we take a look at that equation and we're just looking at x, another way of writing that is these 3 equations up here, that the center of mass, the x-coordinate of the center of mass, is the sum of the masses times the coordinates of however many objects you have over the sum of the masses of those objects. In the y-coordinate, or the y-coordinate is given by doing the same calculation, but concerning yourself with just the y-coordinates of each of the individual objects. And as you might imagine, the z-coordinate, or the z-coordinate of the center of mass, is given by this same sort of calculation, where you have a sum of the mass times the position in z of however many particles you have over the total sum of the masses of those particles. If you think about this in terms of vectors, or in terms of a position vector, that's r, center of mass, that's going to simply be the x-coordinate of the center of mass I cap plus the y-coordinate of the center of mass j cap plus the z-coordinate of the center of mass k cap. And if you put that all together, you have the position vector of each particular particle, r1, r2, r3, r however many, times the mass of each of those individuals over the sum of the masses of the individual particles. Okay, so that's how you're dealing with it. Now, if you're dealing with a symmetrical object or a homogeneous object that has a geometrical center, that is where the center of mass is located. And what I mean by homogeneous object is, well, you could imagine if we're taking a look at this sphere and this side is made out of lead, and this side over here is made out of aluminum, of course the center of mass is not going to be right in the center. But if we assume that the sphere is made homogeneously and entirely of either aluminum or lead, there are no density changes, there's no funny business going on, then the center of mass and the geometric center are going to be one in the same. Again, assuming that the object is homogeneous. All right? You can also have some interesting things happen if you have an axis of symmetry. If you have an axis of symmetry, the center of mass lies along that axis of symmetry. Again, assuming a homogeneous object, you have, if you have something which is symmetrical, let's see here, if you're looking at this disk, you have as much stuff on this side of the disk as you do on this side of the disk. Again, meaning that your center of mass is going to be somewhere in here. What's interesting about a center of mass is it does not necessarily have to occur within the bounds of that object. So if you have a donut is perfectly symmetrical, but its center of mass is in the center of the donut, which is not actually inside where any of the mass or any of the stuff actually is. Another dramatic example of it is this balancing bird. And I really wish that I could show you this demo live, but there are these birds which you can purchase, which you can balance on their beak. And they just kind of happily hang out and they just sort of settle there. What's done is very clever. Basically, you have as much mass on this side of the wing and as you do on that side of the wing. And it is so set up that all of these particles end up having a center of mass right here, which is external to the bird. I'm going to see if I can find any demonstration videos of this particular thing, because if you've ever played with one of these things, you'll notice that when you jostle the bird appears to move about that center of mass, and it appears to sort of recover itself or balance itself back out if you tip it or play around with it. So this is just one rather dramatic example that the center of mass does not have to occur within the confines of the object itself. All right, so let's say that we're taking a look at a three-particle system, and the mass 1, which is this guy over here, has a mass of 3 kilograms. Mass 2, which is this guy over here, has a mass of 4 kilograms. And mass 3, which is this guy over here, has a mass of 8 kilograms. So it's asking us what are the x-coordinate and the y-coordinate of the system's center of mass. Well, we just plug in our handy formula. The x position of mass for the x position of the center of mass, we take mass number 1, its weight times its x coordinate, which is 0, so 3.0 times 0, plus mass 2, its x coordinate being 2 meters, times its mass of 4 kilograms, and the 8 kilogram mass number 3, x coordinate is 1, and mass is 8.0 kilograms. All right, and then we put all of this over the sum of the masses of each of these individual particles, and we evaluate and we find that x in the center of the center of mass is 1.067 meters. Y, we do the same thing. So mass of 3 kilograms, and it's at a position of 0 meters. 4 kilograms, that's mass number 2, is at a position of +1, ys. And then finally, mass number 3 is 8 kilograms, and it's at a position of y of +2, so 1, 2, right? So evaluate, and you find that the center of mass, the y-coordinate of center of mass, is 1.33 meters. So if you were to graph that, the center of mass is somewhere over here. It's kind of hard because I've got a relatively large dot, unfortunately, just to make this visible. But as you can see, it is at about 1.33 and about 1.1, or where I think 1.1 is. If you want to measure this out very precisely, you can go ahead and do that. But just in broad strokes, this is where the center of mass would be. Again, you'll notice that it is biased towards the heaviest of the three masses of 8.0 kilograms. And once again, this center of mass is occurring outside of any of these three individual masses. So if we were to throw these three balls at the same velocity, and we said, okay, can you describe the motion? We could describe the motion by describing the motion of the center of mass, right? I'm not going to talk about this a whole heck of a lot, but if we're talking about the center of mass of an entire body, in the case of a solid body, the particles become differential mass elements, dm. The sums become integrals, and the coordinates of the center of mass are defined as you see here. What this means is you're treating a solid object as though it were an infinitely large number of individual particles. So once again, if you are summing if you are summing an infinite number of infinitesimally small things, that's when you're taking an integral. All right? So x center of mass is 1 over the total mass of the system times the integral of the position x times x dm. So you're looking at the position of each individual mass. We can rearrange this a little bit. If the object has uniform surface density, rho is the surface density. So this is density. Rho is defined as dm by dA, and big M over A. So the density is dm by dA, which is equal to M over A, where A is the area. We can do a little bit of rearrangement, and we find that M is equal to rho times A, and as dm by dA A is equal to m, we can, again, rearrange this a little bit. Then, for example, the center of mass in X is equal to 1 over dm dA times A times the integral of X by dm, right? And similarly, this is what we can fill in for the center of mass positions in X, Y, and Z. And this is where A is the area of the object. We can do something analogous in the volume, or when we're dealing with the volume density. So again, we rearrange to solve for m here, and then we find that the center of mass is given by 1 over v integral x dv, the y center of mass 1 over v times the integral of y dv, and z being 1 over the volume times the integral of z dv. Again, don't worry too much about this. I don't see it actually in the textbook, but I just sort of wanted to show you where this sort of comes from, or where you have a bit more of a rigorous definition of the center of mass in a solid object. All right? So let's go ahead and apply what we've learned about the center of mass. When a body or a collection of particles is acted on by external forces, the center of mass moves as though all the mass were concentrated at that point, and it were acted on by a net force equal to the sum of the external forces on the system. So let's take an example where you have a shell which is fired with some initial velocity, and this shell bursts in two. And it bursts in two right at the apogee of flight, right at the very top of the trajectory. And part of that projectile falls straight down and lands. And then our question is, what happens to that other projectile? Well, what we would expect to happen is this half is falling fairly straight. This other half is continuing to curve onwards, and we can describe the motion of the center of mass, which will eventually allow us to derive where this part of the shell is in relation to this part of the shell, and consequently, how far this part of the shell has gone, or this smaller part of the shell has gone. So we are told that the center of mass continues on its original trajectory. We'll call the distance that it travels d sub COM. All right? One fragment falls to Earth at dCOM over 2. How do I know that? Because the explosion is happening at the apogee when this thing has traveled half of its flight, and it's dropping straight down. It's not actually continuing on a parabolic track. Now, it probably wouldn't happen this way, but let's just say, for the sake of argument, that it does, for the sake of this problem, that it does. So one fragment is falling to Earth at dCOM over 2. The other fragment is going to have to land at 1.5 times dCOM because we're told the masses of the fragments are equal. So in other words, if we're doing a weighted average, if this weight is equal to this weight, or if this mass is equal to this mass, so M1 equals M2, the only other variable that we can play with to account for the center of mass is going to be the distance. So you want it to be that the distance of this further fragment averaged with the distance of this closer fragment will give you the distance of the center of mass. We know the distance of the closer fragment. We know the distance of the further fragment. We've defined that as d sub COM. So the average so the further one, in order to give you that average, is going to be 1.5 times d sub COM. Now, this might look a little bit floofy. This might look a little bit hand-wavy. And look, I'm waving my hands with great emphasis. But let's put this on a little bit more rigorous and a little bit less, shall we say, intuitive. Well, it's still pretty intuitive, but let's be a little more mathematically rigorous about it. So half of the mass, or 1/2 m, is traveling dCOM over 2. All right, so, sorry, this mass actually shouldn't be here. This is a typo. right? So there's the mass, and here's the distance. And then we have this second mass being half of the initial mass, traveling some distance x. Okay, and then that's over 1/2 m, that's the mass of the close particle, plus 1/2 m, that's the mass of the far particle. So we now know that it is dCOM. We know that all of this, averaging is equal to dCOM. We do a little bit of evaluation and rearranging, and we come up with 1/2 d sub COM over 2 plus x is equal to dCOM. So to show how I did that, these masses here are going to cancel. 1/2 plus 1/2 is 1. So we have 1/2 dCOM over 2 plus 1/2 m times x. This mass is also canceled out. So we pull out the 1/2, and we're left 1/2 times dCOM over 2 plus x is equal to dCOM. All right. So if we evaluate this, we find that x does indeed have to equal 3 dCOM over 2, or 3/2 dCOM, which will give you 4/2 dCOM times 1/2, which is equal to dCOM. Okay, so x is equal to 1.5 times dCOM. Let me just once again show you how all of that canceling came to be. So this is a typo. Sorry, that shouldn't be there. We pull out 1/2 m. So let's say that we've pulled that out, right? These add up to 1m. So that's 1m. That m and that m will cancel, and we end up here. All right, and then we solve for x. So again, that's a much, I think, cleaner explanation. All right. So we know this, that x is equal to 1.5 times dCOM. And what is dCOM? Well, that's just a trajectory problem. We're just going to handle this as though the center of mass was moving in a standard parabolic arc. And for that, we already have our range equation. This should be a blast from the past, where range r is equal to v0 squared over g times sine of 2 alpha, where alpha is the launch angle. So this would be alpha, like so. And we know that alpha is 63 degrees. So we go ahead and make our substitutions. The initial velocity is 15 meters per second. So that's 15 meters per second squared over 9.8 meters per second squared times sine of 2 times 63 degrees. And I can tell you already that this answer is wrong. So we go ahead and plug this into our calculator. 15 squared over 9.8 times sine 2 times 63. And dCOM is going to equal 18.6 meters. All right. So we go ahead and we say, because we now know what dCOM is, we presumably can find out what x is. And what x is going to be is 18.6 times 1.5. Again, this should be 18.6. And that's going to be 27.9 meters. All right. So there you go. That's how you solve that kind of problem. We're going to skip the last page of the note packet. This is dealing with rocketry and other things. I think we're just going to kind of move past it. It's a bit of an afterthought in this particular chapter. Just note that one thing that we've seen is that you can actually get a much longer distance or a much greater distance of one of the fragments of your projectile if you actually jettison it. So if we were just looking at where the center of mass was going, that would give us a much shorter range. We'd only be able to shoot 18.6 meters if this were a solid projectile. But by having this shell fall apart and having one part of it fall short, we are able to get a much longer range on the remaining part of the projectile. So by jettisoning something, you can actually get a much longer range, which is a trick that's been used both in artillery and in rocketry for many years now. All right, so that concludes the notes for Chapter 8. I'm sorry that these were a little bit on the rough side. I'll try to make sure that what is uploaded for you to fill in is all correct. So please tune in next week for Chapter 9, which is the rotation of rigid bodies. So you can see how exactly Dom Cobb's top is behaving in the sense of physics. Thank you very much, and I will see you next time.